Okay. I'm gonna try to record this lesson just to see how that goes and see if there's any issues with recording. Um, but let's take a look at solving this here. You may or may not have had time to really sit down and work through this. I know we didn't give a ton of time here, but um, some of you, like me, forgot we had lunch, and you've been staring at this for the last 20 some minutes. So um, let's go ahead and kind of work through this. Now, in my mind, there's two ways to solve proportions. One is cross multiply, and that's the way that I'm going to do eventually, and that's the way that I'm going to encourage you to do. But there's another way to look at it, and I think it's important to understand how this works. Is you have, if we read this like a sentence, it's 2 divided by 7 equals 12 divided by x. Well, if I want to solve for x, what if I end up, instead of dividing by 7, what if I times both sides by 7? So in this case, the 7's go away, and you're left with 7 over 1, while 7 times 12 is 84. And then you have a divide by x left on the bottom. Right? And then the next step would be to undo the divide by x. So what if I multiply both sides by x first? And I end up with 2x equals 84. And now it's a divide by 2 game. Just divide both sides by 2, and you end up with x equaling 42. So that's one way. And it's kind of a longer way to do it. I actually would not do it that way. What I would do is cross multiply. The denominator times the opposite numerator. Well, 7 times 2, or excuse me, 7 times 12 is 84. And then what if I cross multiply the other way? 2 times x is 2x. Notice, cross multiplying is the exact same thing we just did. The only difference is it just saves some steps. All right, so that's the reason why I kind of showed you the first method is we're really doing the same thing, but we're cross multiplying and we get 42 either way. So I'm going to use cross multiplying from here on out. And what happens when I have more than just a number or more than a variable? My recommendation is to put parentheses around each group that's more than just a number. And then we can use cross multiplying. So 3 times 9 is 27 times p. For the next one, when I multiply 4 times 2p plus 5, I'm going to actually ask that you write that step out. And the reason why is the number one mistake kids make when solving cross multiplication problems is they don't distribute the 4. And I've found that if I require kids to write this step right here in green, they see the distributive property, and their chances of getting this accurate or correct has gone up significantly. So if I distribute a 4, I get 8p plus 20. And now it's a real quick two-step problem. Subtract 8p over to the other side. Divide by 19. And p is equal to 20/19. Notice that's not a very friendly number, and that is okay. We're not going to get super friendly numbers every single time. So just so you're aware of that. All right, next one. What happens if there's more than one variable? Well, nothing changes. We're still going to think of this as having parentheses around it. If you really want, you can put parentheses around everything. But what are we going to do? We're going to multiply. 3 times 6 has to equal the product of 2w times w. Well, 3 times 6 is 18. 2w times 2w is 2w squared. And then I usually see a lot of mistakes with the solving here. What comes next? Well, think of order of operations. Parentheses, exponents, multiply, divide, add, subtract. What you need to do is you need to get rid of the divide by 2 first. There's no grouping symbols. So what we're doing is we're trying to isolate the squared. So I'm going to divide by 2 first. And then I have the square isolated. And to get rid of the square, we're going to take the square root of both sides. But when we do that, you do have to remember there are two possible solutions when you take a square root. You get a positive or a negative square root of 3, or square root of 9, which is 3. So I actually have two answers here. We get plus 3 or minus 3. My guess is if you didn't remember that, you got the plus 3 answer, but you didn't get the minus 3. Well, since that's kind of an interesting one, let's check our work. What if I plug W equals 3 back into the original problem? Does that create a true expression? So if I plug 3 in here and 3 in here, I get 6 over 3, which equals 6 over 3. And I could keep going, but those are equal. As soon as I know that they're equal, I'm done. I know that that solution works. So positive 3 is a true solution. Let's check negative 3. What if I plug negative 3 in? Well, up top we get 2 times negative 3, which is negative 6 over 3, equals 6 over negative 3. Those are equivalent. It's just the negatives in their different spot. So if you actually do divide it out, you can see that those expressions are exactly equal, which means both solutions end up working. All right, this is a really big part of what we're doing this trimester, or this unit, is cross multiplying. So a lot of algebra here today. All right, quick quote: "Footprints on the sands of time are not made by sitting down. You got to get up, do something, be active." And that quote reminds me of being active in math. Right now, we have 5 students who did not turn in their proof project from last Wednesday. We started it on Tuesday last week, and then you were supposed to finish it and submit it by Wednesday. Of the 5 people that are missing, I believe 3 of you have started it. You just have to finish it. I also have another person who did not take the Unit 2 test. That should be done ASAP. Conferences are this week, and conferences are going to start as early as today. I can call parents, and I'm expected to call parents for any student that is scoring below a 70%. So if you're below 70%, I have to make a personal phone call to your parents and discuss what you can do to boost your grade up. The number one thing I'm going to say is, did you do the tests? Did you do corrections on the test if possible? And did you do the project, right? Regarding the project, really quickly, the project was out of 50 points. If you mentioned the vocabulary terms in each of the 3 tasks, then you most likely got 100%. I was looking for specific vocabulary items, something like one of the skills that I really struggled with was identifying vertical angles, or given parallel lines, identifying alternate interior angles. We wanted you to be specific about what vocabulary pieces you were struggling with, or which ones were improved through the use of our canfigureit.com time. The other thing was some of you got a 51 out of 50 or a 52 out of 50. And we didn't ask you to, but some of you took it upon yourself to really dress it up and make this a really good visual product. And if you did that, I gave you 1 or 2 extra bonus points. So that's why you may have scored higher than the total. All right, so we are jumping into Unit 4. Unit 4 is really Chapter 6 in our textbook. We're going to cover 3 sections today. 6.1, 6.2 is all about proportions, which is just really algebra. It's kind of what we did in the warm-up. And then section 6.3 gets into the idea of similarity. So I'm going to give you a second to draw the picture. And if you can, I'd like you to solve this proportion for x with the given information here. If you don't know it, we'll go over it in a second. Okay. If you don't recognize it, this is basically the exact same problem, exact same structure as what we did in the warm-up. The only difference is now there's a picture and we have to interpret the information. So here's the first part. What they're telling us is that side length BC, when compared to CB, is in the ratio of 2 to 1. Well, I don't really like this notation for writing ratios. I like to set it up as a fraction because in my mind, a proportion is a fraction equaling a fraction. So AB to CB is equal to the ratio of 2 over 1. Well, wait a minute. We know what each one of these ratios are. AB is 16x. That's the side length. And CB is 24. And that ratio is equal to 2 to 1. Well, we do have to be careful, or we have to think of, wait a minute, this 2 to 1 is this very special term that we're going to call the scale factor. And the scale factor is like a legend or a key. If you're ever looking at a map and they tell you that for every inch on the map, it's equal to 15 miles in real life. Well, they're setting up a proportion, or to figure out how far you would need to travel, you could use a proportion to figure out your total distance you would travel in real life if you knew how far you traveled on the map. This is the same idea. So what do we have? We've got 24 times 2. Well, that's 48. Has to equal, cross multiply the other direction, 16x times 1. And then get x by itself, we divide by 16. Now, you might know this answer. I always like to take time and just kind of show you a way to think of this. If not, you can just play the divide by 2, divide by 4 game, whatever works best for you. If I look at this, I know 2 goes into each one of these quickly. So I might say, all right, cutting things in half is pretty easy. So this is the same as 24 over 8. Well, wait a minute, I could cut that in half. That's 12 over 4. And then I might say, well, wait a minute, 12 divided by 4, they're each divisible by 4. Well, that's just 3. So even without a calculator, you should be able to reduce fractions. You might just have to keep dividing by 2, dividing by whatever's familiar if you don't know the fact right away. So now notice the direction said solve for x. Cool, I did that. It could also say find AB, and if they do, then we just plug 3 in here. 3 times 16 is 48, and this would be 48 over 24 is a 2 to 1 ratio. Okay, these are big. Definitely write this one down. This one tends to stump kids a little bit. Extended ratios. That's when we compare more than just 2 quantities. What if we compare 3 or more? In this specific case, we're going to look at the ratio of the sides of a triangle is 2 to 3 to 4, and the perimeter is 120 inches. Find the measure of each side. I'm a visual learner, So I'm going to draw a picture here, and it's not going to be perfect, which is fine. But I drew the first side length, which I'm going to think of as 2. The second one is 3, so it's longer than the 2. And then the 4 should be about double the length of the 2, just with the idea of the way we can think of ratios. So what happens now? If I have this side length is 2, this side length is 3, and this side length is 4, but if I add them up, that doesn't equal the perimeter of 120. So that means, oh, it's a ratio. Ratios are always reduced. That means there was some factor that was a common multiplier between all of these. So really, instead of 2 to 3 to 4, you can think of it as 2x to 3x to 4x. So now I know that the perimeter of 120, which is all 3 sides added up, has to be 120 inches. I'm just going to add up the 3 side lengths, 2x, 3x, and 4x, and then just let algebra work its magic. Right? Combine your like terms, you get 9x. Solve for x. And I'd like to resist the urge of grabbing a calculator. Okay? Let's play the divide by 2 game. Or in this case, 2 doesn't go into 9. Let's divide by 3. So I could say if I divide this by 3, I get 40 over 3. And 3 doesn't go into 40 evenly, so then I know I'm done. I'm done solving for x, but I didn't answer the actual question. Find the measure of each side. So now I have to plug in 40 thirds into both spots. So what if I put 40 thirds and then I double it? I times it by 2. That's just 2 over 1. And multiplying fractions ends up being 80 thirds. Nothing, it's not the prettiest of numbers, but that works. And then what if I plug in 40 thirds here? 40 thirds times 3. Wait a minute, that's 3 over 1. 3 on top and 3 on bottom are going to go away. I'm left with 40. All right, and then the last one. Let's plug 40 thirds in and times it by 4. That is 4 over 1. That's 160 thirds. And if you were to add all of these up, it'll turn into 120, and that would confirm that x is the right answer. All right. Now, it doesn't just have to deal with side lengths. What about angles? I'd like you to try this one here. Oh, how come we're not cross multiplying? Great question. So notice the equal sign is not in between. If I go back here real quick, look at where the equal sign is when we cross multiplied. It's a fraction equaling a fraction. That's what it is to solve a proportion. Okay, so we cross multiply when the equal sign is between them, but here I'm just multiplying fractions. I've got 2 over 1 times 40 thirds. So we're not cross multiplying here. You only cross multiply when a fraction is equal to a fraction. In this case, we're using our rule to multiply fractions, which is numerator times numerator over denominator times denominator. And that's where the 80 thirds came from. So phenomenal question right there. Thank you. All right, I want you to try this one. The ratio of the angles of a triangle is 1, 2 to 6. Find the measure of each angle. So see what you can do on this one. I'll give you a minute or two. All right, let's take a look at this one. There was a great question that just came up. How do we know what to set it equal to? Right? And this is one of those things you really have to read carefully into what this problem's asking. So here's what I would do. We know that if it's a ratio, it's reduced, right? So 2 to 1 to 6 is reduced. So I'm going to really think of this as 1x to 2x to 6x. There's some multiplier that we have to find. And then it says the angles. All right, so angles are inside of a triangle, and it's angles of a triangle, are 1, 2 to 6. So I'm just going to try to map this out. If I drew a random triangle, this looks to be the smallest one, so I'm going to call it 1x. This would be 2x, and this would be the largest one at 6x. Well, now I'm a visual learner, and the second I draw the triangle and put these items in, all of a sudden that makes me think of what we've learned in Unit 1, the triangle sum theorem. The angles of any triangle always have to equal 180. And that's the thing that our ratio is going to equal. So they don't have to tell us that it equals 180 because the triangle sum theorem already told us what it was. But that's what makes this a difficult problem, right? Is you have to read this and understand what it's asking. So now it's the same kind of work we just saw in the last one. Add up your x's, you get 9x equals 180. If I divide both sides by 9, I get x equals 20. And then to finish the problem, find the measure of each angle. I'm just going to plug in 20 into each one. So 20 times x is 20, 20 times 2 is 40, and 20 times 6 is 120. And if I add all those up, I know that it equals 180 degrees. So perfect kind of example where you have to read a little bit further into the question. And my advice, draw a picture. When I see that picture, it kind of just makes things appear. The 180 in my brain just kind of appears because that's a theorem we've learned in the past. Okay, so that was section 6.1 and 6.2. The big part of this unit is similarity. You don't have to write this learning target down, but we're going to officially start section 6.3 right now. We've already learned how to solve proportions, how to set them up and solve them. Now we're going to look at this idea of how do we use this concept of similarity or similar figures, and how do we solve problems? So you don't have to write this. And we have a little bit of a shortened hour because of lunch, so we're not gonna do the group discuss here. But let's look at this idea of what do you know about shapes that are similar? Well, if I look at these two, it doesn't matter if they're rotated, flipped, turned, orientated differently, but shapes can be similar if they're exactly the same. Shapes can be similar if one is bigger than the other, but look at the angles. If I match the angles up, every single angle that corresponds is exactly the same measure. So similar means they have to have the exact same angle measures, but the side lengths don't have to be the same. Now look at this one. If I rotate this really quickly, you can see pretty quickly that just by checking the top angle, the angle on the shorter arrow is not the same as the angle on the taller one. So therefore, we know pretty quickly that these two items are not similar, but these two items are. Okay, so that was just a visual of what and how we're going to define similarity. So two polygons. We're really going to be focusing on triangles a lot this unit again, but this is true for any polygons. Two polygons are similar if corresponding angles are exactly the same. They're congruent. So the angles have to be congruent, but the side lengths don't have to be congruent, because if they were, then it would be the exact same shape. The side lengths have to be proportional. And we're going to kind of define this proportional as that's the big part right there, is when we say something is proportional, we're going to check and see that it has the same scale factor. If the ratio of sides have the same scale factors, then you know for sure that the side lengths are proportional. So we talked about this before, but similarity in my mind means same shape, different size. Right? If it's the exact same shape, the angles are preserved. If it's a different size, that means the side lengths are proportional. There's a scale factor that relates them. All right, let's try this piece right here. Now you're going to notice something familiar about this problem. Triangle ABC. Look at that symbol. It's different. Right? We took away the equal sign. They're not congruent, but they are similar. So this little squiggle without the equal sign underneath it is going to be our symbol for similarity. The cool thing is we read these angles the same way we did with with congruent triangles. We read the statements the same way. So I'll give you a second to write that down, draw the picture. one of the things I like to do is, even before they ask me any questions, is I like to kind of analyze the statement. So let's think about this. According to this statement, ABC is similar, which means the angles are the same. So angle A has to match with angle Y. That's how you kind of get the orientation, or how you figure out which triangle pieces go together, as you read the statement. And then we know angle B has to be the same as angle Z. So I'm going to put a different marking. Let's do two congruent markings for B and Z. And they actually already matched up C and X for us. So now I know what goes together. And that helps, because the next thing I'm going to ask you to do is, I want you to list off the pair of congruent angles, and then list off the sides of proportional side lengths. We're going to set up a proportion. So I'll let you guys kind of get caught up here, but as you're filling this out, since we know the angles are going to be congruent, go ahead and just list out which ones are congruent to A, B, and C. We're going to do the proportions together so you get it set up correctly. All right, so we kind of already matched this, but we said angle A was congruent to angle Y, angle B is congruent to angle Z, and angle C is congruent to angle X. So nothing special with angles. Angles are congruent if the triangles are similar. Side lengths are proportional. Right? So we're going to set up their proportions. And the way that I'd like to do this, we'll set this up in a second, but read the statement. AB. Let's consider anything that we set up a ratio. The numerator will come from the big triangle ABC, and then anything from the denominator will come from the other triangle. So if I match this up, I'm comparing similar sides. So I'm going to compare AB to the side length ZY or YZ. Some people like to use highlighters. AB over YZ. All right, and then we're going to go to the next one, and we're going to go from B to C. That's in the numerator, and its match would be ZX in the denominator. All right, and then the last one, A to C over Y to X. If you like your highlighters, you can match those together. All right, one other way you could do this is, if we had numbers for the side lengths, you could compare the big side to the big side, the small side to the small side, and the medium side to the medium side, and we'll show you that in a second. But what did we just do? We wrote a ratio of corresponding sides. We wrote how the sides are related by comparing the ratios. let's try using a problem where we're going to actually have to solve things now based off of the statement. So we've got two triangles. We know they're similar because they told us. And right now, that's the only way we're going to deal with it, is they have to tell you they're similar. Starting on maybe Wednesday even, we're going to start looking at how do we prove them to be similar. Definitely going to do it on Thursday. All right, so it's given that EDF and triangle NMP are similar. And then they gave us the side lengths, and we know all three sides of the big triangle, and we're missing one for the small triangle. And at some point, we're going to find out what that value is. But before we do that, we're going to set up the ratio of the lengths of corresponding sides. It's the same thing we just did. We're going to match up the sides that go together, but I'm going to give you another way to look at this that I think is really helpful. Okay. Now, we talked about this where we can use the state, right? ED has to match with NM. And that's an N. But here's another way to look at it. Look at this triangle. The only way that these are going to work is if I match 9 is the smallest side of this triangle. So I'm going to match the small side to the small side. 12 is the smallest side of this triangle. So we're matching small to small. And then I'm going to go to the next one, and I'm going to do DF, which is the middle or medium size, and that has to match with MP, which is 16, middle or the median. So DF over MP, and then that ratio has to be equal to the last one, EF over NP. Well, we don't know this side length, but you can clearly see that this is the big side to the big side. And that will help you when you're solving for x. All right, and it's another way to set up your ratios. It's small to small, medium to medium, big to big. Well, now that we have the ratio of the corresponding sides set up in words, let's actually just plug in the numbers. Let's match those up. 9 over 12, that's the ED over NM. And then what was the medium? The medium was 12 over 16. And then the big to big, well, that was x, which we don't know, over 20. Oh, wait a minute. The first two are just fractions, ratios that can be reduced. What if I divide by 3? I get 3/4. What if I divide 12/16 by 4? I get 3/4. And that means that the x over 20 has to equal the other two, which tells me right there my scale factor is 3 to 4. Now you can write it with the colon, or you can write it as a ratio. I prefer to write it as 3 over 4 because that's how we're going to solve for x. So hopefully you're noticing the benefit to writing these corresponding sides. If I compare to small and big to big, then I get a reduced ratio of 3/4 is equals to x over 20. But the same thing is true if I compare medium to medium and big to big. If I compare these two fractions, then I get the same work after we reduce it. So it doesn't matter which grouping you pick. Since these two are joined together, what if I set these two up? Well, to solve for x, now look at where the equal sign is. It says a fraction equals a fraction. Now we're going to cross multiply. 4x is equal to 3 times 20, which is 60. And if I divide both sides by 4, I found the length of x. That's 15. All right, so we're almost done with this problem. Now they want me to find the ratio of the perimeters. So I got to take the perimeter of the small triangle and compare that to the perimeter of the big. Well, we know that x is 15. We found that already. So what if I add these up? 9 plus 12, that's 21. 21, 36 units, whatever they are. We could say inches, but 36. And then what if I add these two up? 12 and 16, that's 28 plus 20 gives me a perimeter of 48. Right? So the ratio means fraction, of the perimeters. I want to take the perimeter of triangle EDF, and I'm going to compare that to the perimeter of triangle NMP. We already know what they are. 36 over 48. And now you might see quickly what divides into these. If not, divide by 2. Divide by 2. Okay, but I can still divide by 2. That's 9 over 12. Oh, wait a minute. Now I can divide by 3. That's 3/4. Oh, wait a minute. What did we just find? We found that the ratio of the perimeters is exactly equal to the scale factor. And that will be true every single time. All right. We got one last problem that we're going to write down. And then I've got one last problem to show you. We got a couple minutes to do so. All right, so here it is. And actually, I don't even know if you want to write this one down. It's up to you. We're only going to do this one way. But our job is to find the ratio we want to find the perimeter of both pentagons. Well, this one's pretty quick, right? We can find the perimeter of the big one and just add these up. Here I get 30, 42, 57, plus 9 is 66. But then I don't know the perimeter of the small one. So one of the options is to find all 4 of these missing sides, setting up proportions. I don't want to do that. That's a lot of work. We know from the last example that because the pentagons are similar, that the ratio of the perimeter is the same as the scale factor. So that's what I need to find, is I need to compare the scale factor. And the only side length I know on this is 10. But I'm going to compare that to its corresponding side. And this should be better labeled, but you can see the images are the same orientation. So I'm going to compare the ratio of 15 to 10. And then we're just going to simplify. Divide by 5. Divide by 5. We get 3 halves. There's my scale factor, which means the perimeter of the big one over the perimeter of the small one has to be equal to the same ratio of big over small. So we're going to set up 66 over P is equal to the ratio of the scale factor 3 over 2. And it's just the same algebra we've been doing. Doesn't matter which cross product you do first. You could do 3P equals 2 times 66. And then divide by 3. And I think that's 44. And if this was inches, all the other lengths would be inches as well. But there's our perimeter, 44. So I went a little faster through that one. But notice how important that scale factor is. All right, so here's the last one. Right now, if you're at Tartan, we've got 7 minutes until those of you that are going to be on the bus are excused. So if Mr. Christofferson wants to go around, he's going to spray the tables. The spray has to sit for 5 minutes before you can wipe it off. And then as you're packing up, watch this last example. Nobody needs to write this down. If you really want to look back on it, I'm going to post this to Schoology when we're done. So how do we do it if we don't want to find a perimeter, but I want to find a side length that's not part of the full triangle? Well, notice the first part. It's given that the triangles are similar, and we have to find the length of PS. Well, where is PS? PS is right here. Okay, so I'm going to call that X. I want to find X. Well, how can we set this up? There's more than one way to do this. But I need to find a scale factor, and I could use the side lengths. PT has to be compared to PZ, but I don't know any parts of those, so this pairing doesn't help. So what about TR? Ooh. TR is 6 plus 6, or 12. And that has to match with ZX, which is 8 plus 8, or 16. So if I compare 12 over 16, that ratio has to equal the ratio of X to 20. And X is the length PS. Well, before I cross multiply, these are pretty big numbers. Let's reduce this one down. Let's divide by 4. There's my scale factor. Every single piece that corresponds is equal to 3/4 as a scale factor. Now we can cross multiply. 3 times 20 is 60. That has to equal 4 times X. If I divide by 4, I get the length PS is equal to 15. And this is actually called an altitude of a triangle. We didn't go over or learn that yet, but that's how you would find the altitude, is you just compare it to its other altitude and use the same scale factor. All right. I will be at my office hours today from 1 to 2. If you need any help with the project, questions about doing a retake or corrections, I should say, on your unit tests, Here's tonight's homework. There are two parts. It's 6-1 and 6-3. It looks like a lot of problems, but they're really quick cross multiplying for some. You can use this PDF is on our Schoology board, so you can click on that, or you can just look at your textbook or use the PDFs that are in our folder. Just remember, we're on chapter 6 this time. So once you get that written down, that's all I got. Have a great day, and I'll see you in office hours or I'll see you in person on Thursday. Adios.